Thank you. So today we're going to talk about the Chomsky hierarchy. And in order to talk about the Chomsky hierarchy, we need to talk about formal grammars. We've already talked about one kind of formal grammar, context-free grammars. But now we're going to talk about a generalization of context-free grammars, formal grammars in general. And these have the following parts. You have a vocabulary of terminal symbols, which we call sigma. A set of non-terminal symbols we'll call n. A special start symbol s. And then production rules. And you can have different kinds of production rules depending on what kind of grammar you have. So in regular grammars, you have one kind of production rule. In context-free grammars, you have a different kind of production rule. And in context-sensitive grammars, you have yet a different type of production rule. On up to a kind of grammar that is equivalent to a Turing machine, which lets you rewrite anything as anything. So a formal grammar, G, defines a formal language. So we usually denote that as L of G. The formal language corresponding to that you get from the grammar G. So the most restricted kind of formal grammar that can generate an infinite set of strings are regular grammars. And regular grammars come in two flavors. They can be right linear or they can be left linear. For any regular grammar that is right linear, there exists a regular grammar that generates the same strings, that accepts the same strings as that grammar that is left linear, and vice versa. So there's always an equivalence between right linear and left linear grammars. So this is what right linear grammars look like. So you can have two kinds of rules. One, where you rewrite a non-terminal as a terminal, and one where you rewrite a non-terminal as a terminal followed by a non-terminal. So this is what gives you recursion and what allows you to have infinitely long strings generated by a finite regular grammar. So right linear grammars have the same constraints, but this rule here is reversed so that instead its non-terminal is rewritten as non-terminal terminal. It's just reversing the order of those two elements. So all regular languages, all languages that can be described by a regular grammar, all sets of strings that can be generated using a regular grammar have both a right linear and a left linear grammar. You might ask, why are they called regular grammars? Is it because they eat a lot of fiber? Is it for some other reason? And it has something to do with the regular and regular expressions. Does anybody know what the relationship between regular grammars and regular expressions is? So regular grammars recognize exactly the same languages, exactly the same set of languages that true regular expressions do. And as we know, going back to the morphology section when we talked about finite state machines are equivalent also to regular expressions. So these three things finite state automata, regular grammars, and regular expressions are all weakly equivalent. That is, they all describe exactly the same family of languages. So here's an example of a regular grammar. One that generates one or more A's followed by one or more B's. So first we start with S. We have two rules for S. Either S can be rewritten as AS, or it can be rewritten as ABS. And AAS, as we see here, can give you another A, or it can be rewritten as ABS. As here. And then BS can be either just a B, in which case you might have A, B, or it can be rewritten as BBS, in which case you might have a B, or another B, or another B, and so on. So what is the corresponding regular expression? In true regular expressions, none of this Python bullshit. Well, so I said in true regular expressions. So yes, if A has it. So it's A star, B star. The plus notation comes from practical regular expression notations. It's not the original Kleene notation that was used in mathematically proving the properties of regular expressions. So, but it's convenient. So LRG can be recognized, as I said, by a finite state machine. So that means that it can be determinized. Any finite state automaton can be determinized so that each state has at most one arc per terminal. But in order to do that, you may make a very big FSA with 2 to the n new states. It can also be minimized, so you can find a minimal set of states or arcs that accept the same language. So regular grammars and finite state machines are sometimes used in implementing regular expressions. Sometimes they can't be. Why would an implementation of regular expressions not be possible in terms of finite state machines or regular grammars? Right, so if you implement something like look ahead, you stop having true regular expressions. You can recognize languages that are not regular languages, that are not part of L of RG. So you can't use finite state machines or regular grammars directly by themselves to do that. You have to use some other less beautiful mechanism. Well, we've already talked about context-free grammars. They're more powerful than regular grammars. That is, they can recognize all of the languages that regular grammars can, and then some. So rather than having just 2 types of rules, you have lots of types of rules with context-free grammars. They all have in common that you could have just one non-terminal on the left-hand side of the rule. But you can have whatever you want on the right-hand side of the rule. So these are very good for expressing things like bracketing. If you think about like bracketing in a mathematical expression, like 2 times 3 plus 1 plus 5. Can you handle this expression intelligently or describe the set of expressions like this in a restrictive way using regular
That
grammar?
seems very major.
Hello?
It's like 90% success without any complications.
Somebody is talking in the background. Could you mute or talk?
Yeah. Or that day.
Okay. So can you do this with regular grammars? Would this language of mathematical expressions be a regular language, a language that can be recognized by regular grammars or described in terms of a regular expression or a finite state automaton? What do you think? Here's a hint. No. No, you can't get this with a finite state automaton. You can't get this with a regular expression. Why not? Okay, so Chris Fan says you need some sort of memory. And in a sense, that's correct. So you need to be able to know how many brackets you've already crossed. You need to be able to keep track somehow of how many right brackets and left brackets you've crossed as you go through the string. And a regular expression has no way of doing that. By the same logic, a regular grammar has no way of doing that. And if you think about how a regular grammar works and what the possible rules are, then you can see why that's the case. But context-free grammars can handle this. So let's see an example. So here's a context-free grammar for arithmetic expressions with A and B for addition and subtraction. So our bracketing is expressed here by a rule that generates the opening bracket, the content, and the closing bracket. And then you could have any combination of these symbols inside it, either bracketed or unbracketed. So CFGs are more powerful than regular grammars, because any rule that you can have in a regular grammar, you can have in a CFG, but CFGs allow these other cool things. So L of CFG can be recognized by push-down automata. They are to context-free grammars what finite state automata are to regular grammars. And they're like finite state automata, but with a limited kind of memory, kind of push-down stack that allows them to deal with these kinds of bracketing situations. Context-free grammars can also be normalized. This is going to be important to you when you learn about parsing algorithms. So there's something called Chomsky normal form. And in Chomsky normal, you can rewrite any context-free grammar as a context-free grammar in Chomsky normal form. And in Chomsky normal form, there are just 3 kinds of rules. You can have a non-terminal rewritten as null or epsilon. It's an empty category. You can have a non-terminal rewritten as a terminal, or you can have a non-terminal rewritten as 2 non-terminals. So this is Chomsky normal form, and any context-free grammar can be normalized to Chomsky normal form. Sometimes it gets a lot bigger, but it's always possible. So most programming languages actually are context-free languages. They can be described in context-free grammars. In fact, some of them are parsed. They're using context-free parsers. Their formal specifications are often stated in terms of context-free grammars. Can you think of any exceptions? Do you know of any languages that would not be context-free or not be wholly context-free? So Chris Fan says C++. Why is C++ not fully context-free? What part of the language cannot be expressed in terms of context-free rules? Can you tell us, Chris? So even parsing C++ requires solving the halting problem. And the problem with C++ is actually the template syntax. So what something means in the template syntax is sensitive, and how it should be parsed is sensitive to the context in which it occurs. So it can't be described with a context-free grammar. This is, depending on who you ask, a major design flaw. But people seem to program in C++ anyway, and nobody has died waiting for their code to compile or anything like that, I think. So that's okay. There are other examples. So Perl, a terrible language from the past, was famously not context-free. Python would not be context-free. It's not context-free until you normalize out the white spacing conventions. If you replace them with brackets, then it becomes context-free. So it's basically context-free, but you have to take this extra step or go up a level of abstraction. Then you have context-sensitive grammars. Context-sensitive grammars have rules that look like the following, where NT is the thing that's getting rewritten, and the thing that's on the other side is what it gets rewritten as. And what is to the left and what is to the right, that's backwards. What is to the left and the right is the context. So this T and this NT would only get rewritten as TNT when it occurred between these 2 non-terminals. So that's what makes it context sensitive. Or this non-terminal would only be rewritten as this terminal when it occurs between this non-terminal and something. So the left-hand side in context-sensitive grammars can have more than one symbol, but only one of those symbols gets rewritten. Does that make sense? So the others, so there's one that gets rewritten and the others are context, left and right context. So we could think of this as NT, T, NT, NT. You know, put the context back in the right-hand side of the rule. So in phonology, the branch of linguistics that seeks to understand the sound structure and sound patterns in languages has traditionally used context-free rules. And they write them like this. You may have noticed that, we mentioned these before when we were talking about orthographic rules or spelling rules in the morphology section. Same thing. So we can have rules that say things like A is rewritten as B when it occurs. The slash here means in the context of. So when it occurs in the context after X and before Y. So for example, N is rewritten as M before P or B. So these are context-free rules, right? Or context-sensitive rules. The rewrite only occurs in a particular context, but you don't modify the context, you just modify the target, the source to the target. So what is ironic about this? Well, as you might have noticed from the morphology section, we wrote these rules as finite state machines, or as finite state transducers. And in fact, almost all phonological rules that have been described in languages can be implemented as finite state transducers. So we're skipping up using a much more powerful formalism than necessary in order to do this. So context-sensitive grammars, their language can be recognized by a kind of automaton called a linear bounded automaton. They can be a lot harder to process because parsing is expensive, as you might imagine. And there's a lot of spurious ambiguity. So you can have a lot of ambiguity that doesn't correspond to a real structural difference. So we like to avoid these. We like to avoid using context-sensitive grammars where we can, because it introduces these problems. Then there are generalized rewrite rules. So in these rules, you can have any number of symbols on either side, rewrite anything as anything. These are equivalent to Turing machines. And as you probably know, they can therefore be intractable. They're very powerful. You could use them to implement a new Android Twitter client. You could not use them to implement a new iOS Twitter client because Apple has its own proprietary set of generalized rewrite rules that are not compatible with what other people use. So it turns out that we can place all of these different types of languages and all of these different types of automata into a hierarchy. Where the top level in the hierarchy, we'll call it 0, type 0 languages subsume all of the others. And type 1 subsumes everything except 0. Type 2 subsumes type 3, and then type 3, the regular languages, is the most limited and most restricted. So basically, as your restrictions on the kind of rules that you can have goes up, the size of the set of those languages, or the magnitude of the set, these are infinite sets, but the set gets more restrained. So the number, that's not the right way of putting it, but basically, the stricter the rules, the more restricted the languages that the family of the class of languages. The stricter the rules, the more restricted the language class. And in a way, the simpler the automaton, also the more restricted the languages in the class. So this is the Chomsky hierarchy. Now you may be wondering, what about star here? This says mildly context sensitive and corresponding to a thread automaton. We will come back to this. What we want to do is to endeavor to prove that particular languages are or not regular, or are not context free. And we do this using proof. It's called the pumping lemma. Actually, there are pumping lemmas for regular languages and pumping lemmas for context-free languages. I think there's pumping lemma also for context-sensitive languages. So this is the intuition for regular languages from Jurafsky and Martin, page 533. If a regular language has any long strings, longer than the number of states in the automaton, there must be some sort of loop in the automaton for that language. We can use this fact by showing that if a language doesn't have such a loop, then it cannot be regular. So in other words, if you're generating an infinite number of strings, or very long strings, and you don't have some kind of repeating pattern, then you can't generate such a language. If you don't have any kind of loop, you can't generate that language, those strings, using regular grammars. The language has to be at least context-free. So here is a visual illustration. So if L is an infinite regular language, then there are strings X, Y, and Z, such that Y is non-empty, and X, Y to the N, Z is a member of L for all N greater than 0. So y here is in our loop. So we can use this to prove that a particular language is not regular. So is English regular? Well, let's consider some examples. You may find this more or less confusing depending on your disposition. So what about the sentence, the cat likes tuna fish? How do you like that? The cat the dog chased likes tuna fish. The cat the dog the rabbit chased likes tuna fish. The cat the dog the rat the elephant admired bit chased likes tuna fish. Well, when you get up to this point, these sentences become very hard to parse. But the argument is that they're still grammatical sentences of English. They're just difficult to process because you run out of memory. Your stack in your brain, the part of your brain that is parsing these sentences, runs out of space. And so you can't process them anymore. But the idea behind the people who use these examples is that English is not regular. And why is it not regular? Because these sentences have a structure kind of like this. Sort of bracketed structure. So you've got cat, bit, dog, chased, that's not right. Let's erase this and cover my guilt. I think there's a better illustration on the next slide, yes. So you could have a language that has the cat, dog, mouse, etc. 0 more times, chased, bit, ate, etc. 0 more times, likes tuna fish. But if you take the union of this and English, you end up with a pattern where you have n minus 1 likes. So basically, you have a pattern that is a to the n, b to the n. Can you describe a to the n, b to the n using a regular grammar? Or a regular expression? Or a finite state automaton? So you can keep on going without looping, right? There's no loop. There can be no loop. So according to the pumping lemma, this is not, this language cannot be regular. So here are some more examples. The cat likes tuna fish. The cat the dog chased likes tuna fish. The cat the dog the mouse scared chased likes tuna fish. The cat the dog the mouse the elephant squashed scared chased likes tuna fish. The cat the dog the mouse the elephant the flea bit squashed scared chased likes tuna fish. The cat the dog the mouse the elephant the flea the virus infected bit squashed scared, chased, likes tuna fish. How many of those do you like? How many of those seem like sentences of English? Let's number them. Let's give me your highest good sentence. Highest on chat. So somebody like 6. Wow. You have a very large stack. Most people like somewhere here. Two or three. So if it's only 2 or 3, in fact, if it stops anywhere here, maybe 3 on a good day, Kevin says. So if it stops anywhere in this sequence, then you can actually describe the actual language could be regular. The argument that it is not regular, that it is at least context-free, is that these constraints that you're sensitive to that keep you from saying that it's 4 or 5 or 6 are not grammatical constraints. They're not about English per se. They're cognitive constraints. They're about how much working memory you have. So here's the Chomsky hierarchy again. And we have ways of proving whether a language falls into any of these circles, any of these ovals in this Venn diagram. Well, let's return to this star. So we know that some languages, accepting the argument that I've given you, we know that some languages are at least context-free, 2 here. The question is, are all languages context-free? Or could some languages be require a more powerful kind of automaton to recognize them? So the claim that has been made is that there's a level in the hierarchy in between 1 and 2. So the numbered ones are the ones that Noam Chomsky, a linguist and computer scientist, and now, unfortunately, political scientist, yeah, we did say that C++ isn't context-free, but in terms of human languages, are any human languages context-free? Any natural languages? So the argument is that he missed something, and that there's actually this star here for mildly context-sensitive languages. And there are some languages, some natural languages that are mildly context-sensitive rather than context-free. But that maybe no languages are completely context-sensitive, which is good. It would be a nightmare to have to deal with languages that were context-sensitive. So part of the argument for this, or the original argument, comes from Swiss German. This is actually my wife's native language. So I have some recordings of her reading some sentences. So Swiss German is a language closely related to Standard German, but not mutually intelligible with it. That means that speakers of Swiss German can't necessarily understand speakers of Standard German, and vice versa, without exposure, of a few weeks. They can't understand one another. So it's similar, but quite different in some respects from Standard German. And if any of you speak German, then you'll notice that this is the case. So just to give you a sense of what Swiss German sounds like and what it's used for, namely singing children's songs, then I'm going to play you something if this works.
Ich bin ein kleiner Zottelbär, ich bin ein kleiner Stumper. Ich wackle hier und wackle her und tue auch manchmal Gumpe.
Does anybody here speak German? Anybody understand that? So here are some examples of some sentences from Swiss German that work kind of like these center embedding sentences from English, the ones the dog, the cat bit, chased like tuna fish. But instead of going inside out like this, it's not like that. Instead, the relationships are crosswise. Or more accurately, well, you'll see. So this first sentence is
Jan sagt, dass wir dem Hans ein Haus helfen anstreichen.
So who helped Hans, and who painted, what was painted? The house. And you can go even deeper than that. So this is a problem, right? If you can keep doing this, because you can't do this with a context-free grammar. You could do bracketing. This is not bracketing. This is a step worse than that.
Jan sagt, dass wir die Kinder im Hans ein Haus haben helfen anstreichen.
Okay, so the children wanted to let Hans help paint the house. So these are what are called cross-serial dependencies. And it's not something that you can capture using context-free grammars. It requires a more powerful formalism than that. On the other hand, it's not so difficult that you need the full machinery of a context-sensitive grammar. It's something in between. So let's look at the proof here. So we have this string. Jan sagt, dass mir Kind im Hans es Hus handwelle la halfa astriche. Where we've got cleaning stars here and here and here and here. Well, we take the union of this and Swiss German, and you get something like this, where you effectively have a to the n, b to the m, c to the n, d to the m. This is not something that we can do with context-free grammars. But here's the question. Do we care? Now, Swiss German appears not to be context-free. As sequences like A, B, C, A prime, B prime, C prime, where A is licit just in case A prime appears and vice versa, Likewise for B and B prime, C and C prime. These are, as I mentioned, called cross-serial dependencies. And you can't recognize them with a context-free grammar. So I want you to explain back to me why you can't use a context-free grammar to recognize this pattern. Okay, so Abhishek says each dependency that requires remembering something requires some form of memory. And that's true, although you could argue that you need some form of memory with context-free grammars, with bracketing and context-free grammars. But here you actually need some kind of maybe real memory. And not just a stack, but something a little bit more involved in that. So Chris says once you split an NT, a non-terminal, then they're separate. Right. So if you have a non-terminal and you're using a context-free grammar, and you split here, then this can't see this. They're separate. So you have no way of enforcing, so A to the N, B to the M, A to the N, B to the M. You have no way of remembering N when you get here in the structure. So even English might not be completely context-free. This is, I think, really a semantic example rather than a syntactic one, but it kind of illustrates the idea. So it's good to think about. That's the respectively construction. So if you say Alice, Bob, and Carol will have a beer, wine, and a coffee respectively, then you're effectively setting up a dependency between A and little a, B and little b, C and little c. It's hard to argue that this is syntactic exactly. But there's clearly something going on there. There's clearly something semantic. So even English can be context sensitive in a way. So what we have concluded, what linguists and computer scientists who work in this area have concluded, is that natural language is mildly context sensitive. This may not be true of English. English is largely context-free, with some exceptional constructions, like the respectively construction. It is, however, true of Swiss German and some other languages, some varieties of Dutch, for example. Probably a lot of languages. It's just most languages haven't been studied closely enough for people really to know. But even in these languages, the frequency of context-sensitive constructions is relatively low, and they tend to be bounded in depth by memory constraints. So if we go back to the Swiss German example, my wife can get up to here in terms of depth. She can get up to three cross-serial dependencies. But beyond that, she can't do it. So they tend to be bounded in depth by memory constraints in practice. So do we care? Do we care about the fact that languages are not necessarily context-free? Who cares? For your application, like for your project, for many applications, CFGs may be adequate. Even if you're working on Swiss German, I don't expect that you are, but if you are, CFGs may still be adequate. And they have some great advantages. They are computationally more tractable than context-sensitive grammars, even weakly context-sensitive grammars. They're easy to understand and reason about, and the parsers are easy to implement. So we'll talk about this in the next 3 lectures. We'll talk about the CYK or CKY algorithm, the early algorithm, and so on, and how you can do context-free recognition and parsing. But backing up, for a lot of applications, actually regular grammars are sufficient. Since these recursive structures in syntax are bounded by working memory, then actual sentences that people say and write can often be modeled by a sufficiently complex finite state machine. And once compiled, finite state machines run in linear time. This is much better than any of the context-free parsing algorithms. On the other hand, they're flat. They can't parse sentences into nested constituents, except branching off in one direction. The parse trees always look like this or this. Okay. So that's what I have for today. I wanted to ask at this point what other questions you have about the midterm. Or if you have any questions about this lecture. The midterm date is on the syllabus. I would have to look it up. Let's see. It's coming up soon. It's on October 22nd. Midterm 1 is on October 22nd. And it's a good time to start studying. Start thinking about what we've emphasized and what is important in the course. And so if you have questions about what is important, what might be involved, now is a good time to ask. Yeah, so it's about 10 days from now. Oh, to worry about 10 days from now. No, it's something for you to worry about now. It's something for you to start preparing for right now. Because you'll be so much less stressed out if you do it now than if you start now than if you try to cram everything at the very end. I know it's funny. I was looking at the YouTube statistics for this class for past semesters. And always at the very beginning of the course, there's a little spike where everybody is watching the videos, and then it tapers off. And then right before the midterm, in like 2 days before, it skyrockets and jumps up. And then it settles back, immediately drops back down and settles down. And then when it comes time for the final, it shoots up again. But I promise you that your attention will be much better if you don't try to watch all of the videos at once and do all of the reading at once. If you space it out, think about the quizzes, think about the homework, and try to absorb things more thoroughly and more slowly, I guess, if that makes sense. So any questions? So I'm going to throw out some topics that might make good questions. FST question might be on there that requires you to write an FST to do something. Language modeling. Edit distance. We often have some kind of question where you have to solve an exotic form of edit distance or modify, apply edit distance to some kind of task. HMMs, so it wouldn't be surprising if we have an HMM part of speech tagging kind of question. We sometimes do this after the midterm because we have a homework assignment on HMMs and part of speech. But we could do that before. So from the programming assignments, the FST thing definitely would be the case. We wouldn't require you to, would involve a programming assignment. We wouldn't require you to write the FST in OpenFST's language, but we would require you to apply all of the concepts and ideas that you learned in that assignment. The same is true basically of the edit distance. So we would expect you to be able to not write out in pseudocode the algorithm, but execute the algorithms for edit distance, to fill out like a chart or table or something like that. How much concepts versus applications? So there will be both concept and application questions, and it's usually about evenly split. So most of the long questions will have some conceptual component, and will also have an application component. So I would say roughly 50-50, but that's not a guarantee. So there's almost certainly going to be a classification question of some kind that probably involves both fundamental concepts in classification and also application of those concepts to a particular kind of task. So for syntax, there is likely to be a parsing problem of some kind. where you use CYK or early or some other parsing algorithm to parse data. So you have to know how the algorithm works, and then talk about the application of this algorithm to particular tasks. Any other questions? How did, for applications, Chris asks, will we need to trace algorithms by hand, like edit distance of long strings? You will need to trace edit distance or trace algorithms by hand, but we probably won't. We're not here to like test your stamina, so we're not going to give you gratuitously long things to calculate. You know, we're not trying to make you into computers. We're trying to make you into computer scientists, and so none of the calculations will require a GPU. But you will have to trace algorithms by hand, like the parsing algorithms and edit distance, and maybe for HMMs, maybe Viterbi algorithm or forward backward. Anything else? So Wael asks, does context-sensitive grammar have a formal definition? Yes. Does weak, mildly context-sensitive? So here's the tricky thing. So we can talk about mildly context-sensitive languages. And they are the set of languages recognized by a thread automaton. So we can define a thread automaton, and we can define the language with reference to that. It's somewhat more difficult to define a grammar, a set of a formal grammar that corresponds to mildly context-sensitive languages. People have worked on that, and there are actually a number of different grammatical formalisms that formalize mildly context-sensitive. So there's lexicalized tree adjoining grammar that was invented by Aravind Joshi. Who was the person who discovered mildly context-sensitive languages. You know, so LTAG is a formal language or formal grammar that corresponds to this kind of language. There's HPSG, or head-driven phrase structure grammar, which also corresponds basically to the same set of languages. So, and there's CCG, the kind of categorical grammar that also corresponds to this, you know, could be used as a formal definition of this class of languages that we call mildly context sensitive. But it's not as simple as just saying these, you can have these kinds of rules and not these kinds of rules in the way that you can for these other categories. So that's probably why Chomsky didn't notice this class at first, and why it was left to people like Aravind Joshi to discover it. Does that answer your question? Okay, any other questions? Keep the good questions coming. I like the good questions. Okay, if there's nothing else, then we will go. And I'll leave you a few extra minutes to run to the restroom before your next class, or to sleep if you're in East Asia. And I will talk to you next Tuesday. All right, goodbye.